Okay, thank you very much. Thank you very much for inviting me, also for the nice presentation, introduction, sorry. Today, we have organized this lecture by the Industrial Electronics Society Distinguished Lecture Program. This is a program that selects several lecturers to go to, or in this case, go via internet to chapters of the society, of the Industrial Electronics Society. It's a very active program. Basically, it's just organized and controlled by a standing committee of the society. In this case, the lecture will be related to the modular power converters, especially to how we can extend the remaining useful lifetime of these modular power converters, let's say DC to DC or DC to AC converters, explaining the advantage and, of course, how we can cope with some collateral negative effect that the new algorithm. Then, before I go forward, I think that I should say an important remark is this is an international collaboration between several research groups, especially in Europe, but there are people in China also. Basically, we have been taking the best of each group, expertise of each group to have a total group that can cope with a very complex project. Why a very complex project? Because you can see here, the problem of the remaining useful lifetime extension and control requires expertise from many things. The first one is the power devices aging physics. We need people expert in power devices aging physics, how the devices are aging and how we can extend this lifetime. Of course, we need some people experts in active thermal control method that will extend this. Basically, we need also, of course, power electronic applications, power electronic control and modulation, and very important, the harmonic analysis. So now we have people, as I said before, this group of people are working, contributing with their best expertise. In any case, we are open to more people that are interested in this, and I hope that I can convince you that this is an interesting work. And if you are interested in working on it, please contact me or one of these people in the list. Okay. Let's go directly to the presentation. Today, we will start as usual with an introduction. Later, I will define several concepts related to the thermal behavior of the power electronic components, mostly devices, capacitors. Second, or later, we will follow an explanation or a brief review of what is a modular converter, the basic concept, the pros and cons, and how we can apply some techniques to extend the thermal management for this kind of converters. Once we know that, we can go directly to show a couple of examples, one for DC to AC converters, another for DC to DC converters. Finally, we will draw the conclusions where I will show you the most important references for the topic. Okay. Well, don't forget that when we are designing a power electronics system, we need to think in the cost, the benefit, and the risk we have. That is, we need a very complex trade-off between the cost, that is the capital initial investment, and the operation and maintenance cost. Both have to be carefully taken into account in the balancing. The benefits that we will get with the design is about if we will have low volume and weight, depending on the application, of course, the power quality to connect to the grid, fulfillment of the standards, if we want to connect to a power grid, the efficiency, and of course, if possible, the off-the-shelf design. All these things will have an influence in the operational and maintenance cost, and of course in the initial investment. And the risk, the robustness and the reliability are very important, but it costs. So we have to take into account that a robust system may cost more, but the operational cost will be lower, same for the reliability and fault tolerance. So in summary, we need a trade-off. Normally, it's a complex trade-off between all these things, and we always need to take this in our mind when we are designing a new system. Continuing with the introduction, there is nothing new if I say that in the power grid we have connected today thousands and thousands of power electronic converters. For instance, the converters that connect the renewable energies to the grid, the energy storage to the grid, to complement especially the renewable. In the industry, you can find a lot of motor drives. In the transportation, locomotive and electrical vehicle charging, more recently the data center, and many others related to ancillary service and all these things. So the problem is that the maintenance, normally taking into account that there is a growing capacity, will be a cost, an important part of the operation. In this case, you have to see some case where the wind turbine in offshore, you need to move a platform, many things. So it's very costly. If we say that there is a growing capacity, then the safety is very important, because as big is the capacity, and large is the capacity, the more significant impact after a failure. So we have to be very careful about the failure and the maintenance. The cost of the energy, of course, will be the installation, operation, and maintenance divided by the operating time is what it will be the cost of the energy. Then, if we improve the reliability, that is, if we increase the operating time, then the cost of the energy will be lower, which is very, very important in this case. The question is, which are the most critical components in a power converter? Let me show you one example for solar PV power system failure. In this case, we see power, the unscheduled, the number of unscheduled maintenance events. So you can see that the PV inverter in solar PV, remember, is an example for PV, and the panel stand both were approximately a little bit more than 50%. But this is probably not the most important thing. The most important thing is what is the cost by the system. And here we see that the PV inverter stands for almost 60% of the money that we had to spend in the maintenance. So the power inverters are very, very important, and we should think carefully how to design to avoid this cost is very high. Reducing this, we will reduce the total cost. So in a power converter, what are the most fungible components? Basically, in this survey, you can find this data. It's a bit old, but I think that it continues to be more or less valid. Then the power devices plus the capacitor stand for more than 50% of the total failures. So we can focus in this kind of semiconductor and capacitors in the power component. So let me explain a couple very briefly the thermal behavior of power components. Let's start with the devices. In case of the devices, you have a device like this with a case, the base plate, and the heatsink, and inside there are several bond wire connecting parts of the circuit, which normally may be several silicon wafers, and in this case, we have several soldering that in the microscope you can see like this. In this case, due to the medium of cycles, thermal cycles, extending, compressing, extending, compressing the device, then you may lose the soldering. So this wire is useless for conducting because it's disconnected. This is what we call bond wire lift-off. There is another cause in the soldering between the silicon and the plate, the copper or the alloy copper. Then due also to the same problem that the fatigue of the solder joint, then we may have a soldering. So if we have something like this part of the silicon is useless. So all the current has to flow only by this small part. So basically, it will kill the device sooner or later. Okay. In summary, you can read this references for more details. The repetition of the thermal cycles is the cause of the expansion and contraction of the materials that will create a problem sooner. It's a question. Okay. Let me introduce you the concept of power profile. Imagine an electric car that, of course, depending on the condition of driving or the wish of the driver, you may have a current by one semiconductor or a group of semiconductors, positive, negative. If you are recharging, it's consuming, where you have more or less, depending you go up in ramp, down, up. So every second, every minute, you will have a different value. So this is called the power profile. But we are interested in the thermal cycles, because the power semiconductor aging depends on the average junction temperature, the number of thermal cycles, and the deepness. So we need to know the temperature in the junction. In this case, we may have in a different time scale the temperature, how we can measure it with the thermal camera. You see that in this point you have a very hot temperature. This is intermediate, and this one is in the low value. Then what happened? That the mean value of the temperature will be more or less like this. It's evolving slowly. The number of cycles, we can count the cycles, all the cycles, and the deepness of the cycles can be controlled here, or counted here. So, looking at this, we have information to predict the amount of thermal cycles that the device will survive of the lifetime, in other words. Then, in the industry, it's very difficult to open the case and see with the thermal camera. This is something that we can do in our lab, but in practice, probably we cannot measure the temperature here in the junctions. Okay, so we need something that using an indirect measurement, for instance, the temperature in this point or in the case, can be we can estimate the temperature in the ocean. So using a model that can be this tower model or the Foster model, that using an electrical analogy, this power losses will be similar to the current, and the voltage at this point will be the temperature will be similar to the voltage. So solving this circuit implies that the temperature in the junction can be calculated if we know this impedance, the power loss, and the case temperature. This can be done by the manufacturer of the device, or we can open it and do some measurement using one of these two models, Cower or Foster. The losses is our circuit, so we know the losses, and the case temperature can be measured easily using a sensor. So with this, we know how to estimate the temperature in the junction. Then, as we may have a profile like this in the temperature once that we apply the model, and of course, we need to translate it to this to number of cycles till the failure. The number of cycles for lifetime of the lifetime of this or this device can be given by the manufacturer in a graph like this one. This measure, this gives us, taking into account the mean temperature in the junction, this is for 77.5, the next 90, 102, and 125, that is the max. Then, taking into account the number of the deepness of the temperature cycle, will give us an estimation of the number of cycles to failure. If we are not so lucky to have these curves, then we may use some models that can be explained here in this reference. Basically, it's the Coffin-Manson model and the Norris-Lantern. Both of them give us the number of cycles till failure, depending on several parameters related to the temperature and so on. Then, now, how is the total process explained in this paper? But when we are willing to have an estimation of the lifetime. So from the vision profile, we can estimate using previous models. We can estimate the profile, the temperature profile. With a rainflow counting average, we can count how many cycles the device has been working. So this is what is the actual number of cycles, and this is the total using this table, all the models of the Coffin-Manson Norris-Lantern. Then we have all the total lifetime, the total possible lifetime, and the current number of cycles that it has been working. Then with this, we can find the difference or calculate the damage as the relation between both. Then we have for one device, what will be the lifetime expectancy, depending on the previous work for the device. This was for devices like IGBTs, and this is for the capacitors. The capacitors can have, or we can find a great variety of technologies. This is only for one manufacturer. There are many others, and the most important factors are those voltage rating, the capacitance, stability, and so on. But we will focus especially for the purpose of the lifetime on the equivalent series resistance. Why? Because all the current will flow by this resistance. So we will have Joule losses inside the capacitor, and this will create something, an increase of temperature that is very important, as we will see later. The ESR may be almost constant with the frequency, or will be very, very different with the frequency, with the harmony. This is a model that almost in all the references is used and explained in this reference, but there are other models that we will focus on this. Basically, this is giving us the number of life cycles that the capacitor will survive after applying these conditions. And the conditions are the nominal lifetime and the nominal conditions. This is the current voltage, the rated voltage, a coefficient that normally the manufacturer will tell us for each capacitor technology, and the others are other parameters. But the most important is this for us will be this one, that is the temperature inside. Some manufacturers included a temperature sensor inside or not, but depending on that, we can use as previously a model. Well, one important thing for this presentation is that when I have used a formula and will present the same formula later, I will mark in blue so you can follow easier the presentation. Okay. This is the formula that or the expression I explained before, and we will see how we calculate the temperature. As I said, if you are lucky and have a sensor inside the capacitor, you don't need to do this because you will get direct measurement of this. So the temperature inside the capacitor can be calculated multiplying by the thermal temperature, the thermal resistance multiplied by the losses, assuming the ambient temperature. The losses can be calculated as the Joule effect in all the ESR. Maybe depending on the harmonics, or if the harmonic this is constant, then we will take this out, and this will be the RMS. Okay, then let's go. Once we introduce the thermal behavior of the two more important devices and capacitors, then we can go directly to the modular converters. The basic concept of a modular converter is that they can be connected in parallel to have a higher current, and series to get a larger voltage. Also in a mixed between series and parallel to increase the power. This is something that we will use a very simple. Normally, the blocks, power electronic building block will be very simple, as I will explain later as examples. So examples can be, for instance, for series connection, we may see the modular multilevel converter, in this case using one positive and negative cable to connect two distant grids, 1 and 2, the common coupling point, and two grids to transfer power in one center or another. So basically, This is what is called high voltage DC transmission. Or another example, probably better known, is the motor drive. In this case, showing a straight edge bridge. These are only two examples. Of course, we have many examples. In this case, from this from the grid, is the point. From this grid, we connect a motor. So this is the motor drive. In the parallel connection, we have one example with a multi-string photovoltaic system, where we have, in this case, three, but maybe more than three string of panels composed total plant. Then each of the string has its own DC to DC converter, and in this point, we sound the current to have more power and simpler devices. Another example is this one, where we have a wind turbine of high power, and we distribute the converters in several in parallel. This is another possible application. And finally, a mixed one parallel series. In this case, we have the input in parallel. So this is the low voltage with high current, and this is high voltage or medium voltage for lower current. So any combination of this can help us for this. What are the main features, advantage and disadvantage, pros and cons? First, of course, there is an inherent fault tolerant capability. If in one of these modules it fails, we have a lot of other modules in series that can continue working. So we can consider it a fault tolerant capability inherent. The output waveform and have enhanced quality. As a consequence of this, the cost of the filters is output filter is cheaper. Of course, the reduced maintenance cost is lower because we don't have to change all the converter, just only the default, the one with faults. There is a standardization in the PEVB design, so we can use for other things like this, especially for the firmware. That is an important part of the converters. But of course, there is not everything is positive. So we have some disadvantage. For instance, we have a higher initial capital and operation cost. There is some more complex hardware and software design, including the controls and the modulation. For the modulation, well, if we said this 50 years ago, it's true. Now we have a very good algorithms that are not much more complex, or the complexity is very low. There is a large number of sensors, power converters, it's true. And there is a bigger size of a non-modular converter. This is also okay. In spite of that, modular converters are being used more. But now, with this basic concept, we can go directly how we can apply a thermal management method for the modular converters with the idea of extend the remaining useful life. Okay. Imagine a converter is formed by n cells, and each of the cells will contribute to the total power equally. So we have equal share, that is the total power of the system divided by the number of cells, will be the power that we assign to each of them. So all this power, P1, P2, and so on to Pn, is the same. Okay? That is perfect. When you design one new converter, it will be perfect to work on it. But what happened after several months, several years working? One of the cells may fail, like in this case, cell number 4. So we need to take it off, find the faulty device, find someone to repair the module, and once it's replaced, it is sent back to the store to be replaced and is ready to be reused. So at the same time, or before this, we replace the cell by a new one that maybe zero timing, so fresh cell or not. Maybe one of these repair with more time. So after this, another cell may fail, and we do the same process, another one. So we will have very different cells that is completely different from this. This, all of them were exactly the same, and the expectancy was the same, statistically speaking. After several years, we have something that we know, because we know that there are differently aged cells. We can continue with this policy using exactly the same distribution, so equal sharing. But my question is this optimal or not? Of course, no. And we will see why. So we may redistribute the power in such a way that the total power is the same. There is no increase or decrease because the system is asking for a total power. But we may increase the power in this cell, decrease here, this here, and so on. What is the advantage of doing this and how we should do it? Let me show you. Imagine a simple case where we have only 3 cells, or convenient, but we can explain with more. Imagine that this cell is an aged cell, while these 2 are fresh cells. In this case, we are using a age bridge with a 3 level as a PVB. So if the same power is applied to all of them, then we represent here 3 powers at the same level. Okay. This will imply that the temperature in the 3 cells will be the same. But as I said before, the lifetime is not the same for them. So the fresh cell will have this lifetime, and the aged cell will have this lifetime, maybe half or whatever. Then what happens if I apply? What is the system? The system lifetime will be the width length. So will be the lambda 1. The system will fail when the cell 1 will fail. Then we may do something to help this to survive more time, and consequently the failure of the system will be late. Then what we call our routine will be that the system or the total power will be the same, but the cell number 1 will receive lower power. Consequently, the other 2 will have an increase. Yeah. In such a way that both will be increased partially, and this will be decreased in the same amount that the sum of the other 2 is increased. So this will imply that temperature will increase in the fresh cells and will decrease in this. More power, more temperature. Less power, less temperature, less losses. Then, in this case, we will have an increase of the lifetime for this cell number 1, and a decrease of the cells 2 and 3. Then the system, what is more important, will have this increase. In other words, the maintenance people will go to work after this time, maybe more or less. Okay, the explanation indicated is in this paper, and in the same paper you can see a simulation, a Monte Carlo simulation, depending on what is acceptable in the industry. For instance, if the industry is like aeronautics, accept only 1% of failure probability, then we can see that using the thermal routing, we get 2 years of increase. So the maintenance should be done two years later. If the system or the industry is related to something that can fail and we can accept 10% of failure probability, like in renewable energy, then the increase is only 1 year. It's good. If in 1 year we don't need to spend money in keeping it under maintenance, it's much better. Okay. The problem is this free? We have to pay something for it. Let me see. Probably you can imagine that, yes. Then let's see how we apply to a DC to AC converter, a modular, of course. Which one? It could be this one, MMC, modular multi-level converter, or cascade HBridge. As most people are used to say CHBridge, I will use this as an example. Normally, this is the module that is connected in series. The current by the one phase is common for all of them, so the different power is made by using a different voltage in each of the cells. Okay. This is the normal way to work, supposing that all the DC volts are the same for them, and that we have similar voltage as set up for a reference for the 3 cells. Then using this simple control, that using the same control or reference for the 3 of them, but using different carriers. Then we have for the first cell number 1, VA1 is calculated using these switches. So when we close 1, we open this one, same for this. Then we use a carrier like this and 180 degrees for the carrier displacement, and we get something with 3 levels. This is well known, I hope. So if we do the same with the others, then we will get a summation of 3 levels. But look that we are displacing a little bit the carriers. So exactly we use 180 degrees divided by the number of cells. This case N is 3, so we use 60 degrees from one to the next one. In this case, we see that we can find 7 levels. Okay. Perfect. This is the balancer, and means that all the cells have the same voltage as reference, so all the cells will give the same power because the voltage is if the current is common for all of them. Okay. Let me see how we can see in one of these modules how is so one of these, by the way, of course, the scale is still 100 volts here, and here is 300 because it multiplied by 3. We're assuming three things. Then the analytical expression of the harmonic can be found in this book. I'm sorry, I don't have too much time to explain the details, but the harmonic K is calculated by using this formula. That is well explained in this book, and the way is very good. Then the harmonics can be classified in groups from n equal 1, n equal 2, and so on, so on. Then inside each of the groups, we have a second index, which is n from -2 to 3, and the number of the harmonic is calculated with this formula, where n is the number of the group, n is the position inside the group, and r is the modulation index. So the relation between the Fourier frequency and the sinusoidal frequency. In this case, this is the formula that we can calculate in function of n and n, and the amplitude A is depending on the modulation index, and the Bessel function is. So this is for 1, okay? V whereas Vx is the DC voltage. Remember that in this case we are using the same, but maybe different. And of course, we may have more. Okay, where X is the number of the cell. Then we write here again, and this tells us make 1 equal to 7. Then we have to solve to make it this equal to 7 and manipulate a little bit. We have something like this. It is not easy to solve this part. Okay, it's the real part and the non-real part. Equal to 0. Then, in balanced condition, things are simpler. There is only one n, there is only one VTC. Then it's simpler like this. In this case, we can see that if we apply the conventional carrier phase displacement angles, we get that some of the n are equal to 0. Then we may, if where n is equal to n s to 1 till n minus 1, all these n are self-independently of the value of the number of cells n. Okay, so this is, explain why people use this formula to calculate the angles in a balanced way. But what happens if I decide to change this by using the ATC? Well, first, these are the harmonic that we can see in this case for 3 cells. So we have the harmonic is in double frequency for 1 kilohertz, and this is the total with 3 cells. You can see that the TAT reduces from 54 till 18.9. This is the VAB line box. So this is good when it's balanced. But imagine a case where during these 2 cycles we have a balanced situation. And after this time, we decide to apply the algorithm for the ATC, the active thermal control. Then each of the cells, in this case, there are 4 cells to show the example. We apply different voltage, so different power to each of them. Without the ATC is in blue. This is the waveform in the output. But these are the references. These are the output as it is modulated, as it is 4 cells, so we have 9 levels. And what happened here? In the blue, there is in the balance, there is no harmonic till the 8 kilohertz, around the 8 kilohertz. This is very good because it's balanced, so all these disappear. But unfortunately, when we apply something different, there is a lot of harmonic here. So we solve one problem, that is the lifetime extension, but we will pay a lot for the filter. Can we do something? Yes, I think so. Let me work on it. The explanation why is open. Sorry. The explanation is because in one of the harmonic, this is not a three-phase system. We have three cells in this case. The harmonics have 1, 2, and 3 of each of the cell with a 120, 100, 240 degrees, as you can see here, at different amplitude. So if all of them have the same amplitude, there is no result. But in this case, we see that there are different values, and consequently, there is a resultant. This is the harmonic that we see here. One of these, it happened to all these harmonics. So, what can we do? Imagine that instead of using the angles 120 and 240, we change to 5.2 and 5.3. We need to calculate. In this case, the result is 0. As you can see how changing the angles, we can make the result smaller or even 0. So it's a simple problem for a simple geometrical problem for one harmonic. So we can try to solve this using two approaches. One is using the fundamental frequency harmonic decretion that we saw before, or the sampling time harmonic decretion, the CHV. If we bring here again the formula that we put before, or wrote before, for considering one example of n equal 3, then we have that the dominant harmonics are in n equal 1, n0, and 1. So we can make these two harmonic equal to 0. We have calculate two angles. They will give us the solution of this will be this one. So it's easy to calculate new angles. With these new angles, all these harmonics disappear, are cancelled. These two only. So in this case, the angle is, instead of 240, is 258, and instead of 120 is 126.3. So it's a small step. We have considered some of the harmonics, the filter will be cheaper. But if we do in another way, using the harmonic of this waveform directly, then the Fourier coefficient can be calculated like this, taking into account that it will be periodic at every 2 pi in the fundamental frequency. Then the harmonic, this is the Fourier series, how we can sum more and more harmonics will be closer to this. Then we can calculate the harmonics or make this equal to the total waveform, assuming some harmonics normally to infinity, but in principle we have this, and the content related should be like this, where this is the value that we have here. Okay. In the case that we have three cells, then we can simplify the equation and solve this. Then the new angles this is in the literature. In one of our paper, I will about this later. I'm sorry because we are a bit late to explain the details. So basically, the two angles can be calculated in real time using this formula, where x are here, so on. Then we can apply and we can compare several cases. This is the balanced operation, and we expect all these are 0. When we have unbalanced operation, in this case, is using 3 cells and 3 different modulation index and 3 different voltage for each of them. Then we have the harmonics using the conventional angles. We have all these harmonics, and using the new angles that we calculate with the formulas in this expressions, then we get all this practically equal to 0. This means that we have calculated each cycle the new angle like this. Okay. Okay. But still, we have even in this frequency even worse results. So we are solving this part and not this one. So we have something that we have to find a trade-off between what we reduce and how is the filter. In principle, this is better because the lower frequencies are reduced, so the filter will be more cheap. Okay. Okay, we saw both cases, and the main concept is how to deal with several harmonic groups, because we are working only with one in this case, and how to extend this for more cells. If we have 4 cells, we can apply because there is no analytic solution for that. So how we can cope with all this? We go back to the formula again. We write again the same equation that we had before, remember? And as we know, all the harmonics, no matter how many cells, because it's 10 in general, okay? Then we can use a minimization of defining a cost function. This means that the harmonic to be minimized are calculated in a similar way of that THD or weighted THD, depends on what you want to do. And or we use the H as we define here, or with this one. Okay, then any mathematical search algorithm can be used to calculate the minimum value of this cost function. Making this minimum, we will have the minimum for the filter. Then I'm using the change in market algorithm around here, but any other algorithm can be used. We're using it because it's simple. We have experience on using it, but and also give very good results. So then, as an example, we may use several cases or scenarios. First is using 4 cells. Second using 5 cells, and third using 6 cells. The equipment is here, and you can see here the values for the 6 CHP and the control. Then randomly we should select several values, a set of values of the DC voltage, and for instance here 50, 60, 40, 40, 60. 15, any values, okay, and different modulation indexes, so we can have experiment, repeating the experiment many times, and basically it's the same. Then in the first scenario, that is with 4 cells, we are able to reduce a lot this part and not much in this frequency, the 4 kilohertz. In the second, for 5 cells, we can find that we reduce a lot in both cases, and in the third scenario, we reduce all of them significantly. Then here is the convergence. In this case, the objective function is the weighted THD, how it reduces in practically 4 iterations, taking into account that with the microcontroller that we are using in 4 iterations of 100 microseconds, we get the convergence, and now it's practically stable. Okay. So the angles are these, for in this case for 4 cases, for CHV. Okay. So we have to calculate every fundamental period first, but in the steady state is constant, only in the changes we need to spend most. So this was an example for the DC to AC converter at CHV. For the active thermal control of DC to DC converters, we can do the same. Here some multi-stream PV system on the other example where we split the power in this case in 3, but of course this can be done with more. Then we can do similar things. Let me go to something like this first. Then we will the control system to decide what is the power of each of the converters in parallel. Then we calculate the state of health of the lifetime, and we say in this low cycle control loop the temperature that every converter will have. Then with this we calculate the power that or the fraction of the power that each of the cells will have, and later we go to a power calculating loop, calculating the duty cycle for each of the. So we have here a low dynamic, and here the high dynamic as usual in power. In this case, we may have 2 cells that without applying, we decide to reduce 1 degree in this cell and increase the other. Then, for instance, this is the case temperature by the junction. We increase in 2 degrees and decrease 4 degrees in the IGBT or the diode, or the total power is like this. So we are applying after this moment the APC. Okay. Then in this case we have another example with 3 converters working. How they evolve in dashed line is maybe can show different. This is for no ATC, and this is with ATC. So we can move this module, extending the lifetime and reducing the lifetime of the other one from here to here. Basically, we get an increase of 24 months in this case. Okay. And again, has a problem. Probably yes. Let me explain. If we have 3 cases with a similar, this is what is called interleaving. We will use, in this case, 120 degrees in the displacement of the 3 currents in this 1, 2, 3, and then the harmonics will be like this. In this case, is with frequency 4 kilohertz with 3, we get only the harmonic corresponding to 12 kilohertz, so the filter is relatively cheap. This is the waveform that we get with this one in detail because we are summing up 3 of them. Okay. What happens if the currents are different? For instance, this is close to 40, this is the same, and this one is below 10. So we have something like this, which is not so nice as this one. So obviously the harmonics will be different. In fact, we have a harmonic in 4 kilohertz and another in 8. The question is, should I be concerned? Remember that this is connected not to the grid, because there is a DC to AC converter later. So in principle, these harmonics will not affect significantly to this. But these harmonics will circulate by the capacitor. Then we studied the problem in the capacitor. Again, I repeat in blue the formula that we explained before, and we have to calculate here. Then this is the waveform. Then we can calculate how is the harmonics, or how are the harmonics in this waveform. Okay, and again, we are assuming for simplicity that all the ESR is constant with the frequency, but of course it's going to be done with a different numbers. In this case, then we can calculate the harmonics that are taken from this formula, and finally we can do apply the optimization of this function. Okay. We have several cases in this, to show. In this case, 4. The first one is the balanced condition. The second is the unbalanced case with conventional angles. The third one is the same as the previous, but using the iterative method to calculate the angles, trying to minimize the group M equal 1 or group M equal 3. In this case, for the n equal 1, we find 2 points where there is no harmonic in group L equal 1. We take 2 solutions. One 133 degrees, 240, 2020, 100. In the case where we are trying to minimize the harmonics, or make zero or the minimum in 3 groups, so we work with all the frequencies till 3 times the fundamental frequency of the barrier. Then we have a solution that is not zero, but is small enough to consider it interesting with these angles instead of 120, 166, and so on. Okay, then we can show this and the result. In same examples, using this, we will have several examples using 2 different inductor, 3.6 and 1.8 milliamperes, and different capacitors with different thermal resistance of 2 or 5 Kelvin per watt. Then, in case 1, we see the difference. This is for the 3.6 milliamperes and for 1.8. Both cases are very nice. In case 2, that is in unbalanced with different with the classical method, we have something that is very ugly. In case 3, minimizing 1 group of harmonic, or case 4, minimizing 3 groups of harmonics. How we affect group? We work with the 3.6 milliamp inductance, we have that taking as reference the case number 2, we get a reduction in case number 3 of 329 in this formula, so the RMS, the current, the harmonics, and here practically the same. The temperature will depend on the thermal resistor of the capacitor. Then we have this temperature 31, and the increase is 4 degrees in this case with the good capacitor, and with the bad capacitor, the decrease is approximately 8.3 degrees here. If we do the same with the other instance, then we get this value that are more or less. But you think it's so important to reduce 3 degrees or 6 degrees. It's so important. Well, let's see. If we see the increase in the lifetime, taking this as reference, in all the previous cases, we have very important increase in the lifetime. In this case, it's almost at 80% more, 77% more lifetime. So this is very important that we can do this in the DC to DC converters connected in parallel in Italy. Okay, of course, one detail is you have here. If you have here a string of TV, probably the difference will come from the sun and from the condition. So this can be applied only in case that you are in control. Okay. So you have to be careful. In any case, there will be a reduction for sure. Okay. It's for free. Why? Because we do nothing, just to change the modulation method and the calculation of the angles. Okay, conclusions. Well, as I explained you, the ATC via power routing is a very effective method to manage the remaining useful lifetime of all the power devices involved, the capacitors involved in a converter. Our converter can be applied, as we saw, only 2 examples, but you can find many other examples for both kinds of converters. It's very well suited for fault-tolerant operation. The goal is to reduce the maintenance cost. Of course, this introduces low frequency distortion, but reduce the lifetime of the output capacitor, and of course, distort the output waveform. But fortunately, the variable angle modulation method mitigates this error for free, reducing the cost standing. This is very important. These are several references that we have published recently related to this, and in this case, is the explanation of this. Many of the figures that I explained are taken from our references. This another one, by the way, we got the expected hour, how to explain this. In several of the cases, I have put this so you can go directly get the reference. Another one is this is for explaining, in this case, the reliability for the concept of ATC and power routing. These two are related to the DC to AC converters. Several cases where we optimize the operation of the this is for DC to AC converter. Remember that you can go directly to this or go searching by this. More these cases for the DC to DC converters, or changing the different parameters we can place. This is not for modular. This is another application to reduce the common mode voltage in a motor. I have no time to explain all the things that we are doing, but in this case, you can see that we reduce the common mode without in a classical converter. We can do, of course, in modular or other. This is how we can optimize at the same time. It's not explained in the presentation today, but just if you are interested, you can see this paper on how to minimize the leakage current, optimize the current injected in the grid, and the common mode voltage here. And finally, there are more references, but finally, as I am editor-in-chief of this new publication of the IEEE, is the Open Journal of Industrial Electronics Society. Just remind you that if we are receiving papers, we receive for the first time an impact factor of 5.2 this year. We promise a rapid turnaround, 4 to 6 weeks from submission to final decision, with yes, no decision, so more or less. We use a single blind peer review. There is no page limit online, and it's called open access. It's important to say that the IEEE supports the evolutionary publication. That is, you may have a very preliminary version in a workshop. Later in a conference, you can present a better version of the paper, and finally the journal paper should be elaborated. Of course, the paper cannot be the same. You need to cite the conference paper, and your contribution must be clearly clear. The open access article processing is this amount now, this year, will be the same next year. We have a applicable discount for reviewers, technical committee members, 20% for IAS members, an extra 15% for IAS per corporate paper. From my side, this